I've created some construction lines on GeoGebra because I think that I can illustrate the idea that 6 congruent equilateral triangles will have the same area as one isosceles triangle that has particular properties. So let's see. I have an intersection point of the x and y axis here at the origin. I have a line at y equals 1.73, which should give us a height of about square root of 3. And I have a side length 2. So I should have a 30, 60, 90 triangle here. Let's measure one of these angles. And let's see, 59.97. I'm going to go to options, rounding, 0 decimal places. I now have a 60-degree angle. So I'm satisfied that with some error, this is an equilateral triangle because of the height I've used and these parallel lines every 2 units. So what I'd like to do is use well, I guess I could use the reflection tool. I was thinking that I was going to rotate these around, which would be kind of fun. So let's do the first one by rotating this figure around this point, I don't know, 180 degrees. What will that look like? And I want it to go left. So that's counterclockwise. So that's too far because I wanted to land in this box here. So let's undo that. And are you picturing what I would have to rotate? I noticed that my rounding changed, so I'm going to go back to 0 decimal places. So what do you think? 90? Let's see. Rotate this figure through this point. Yeah, that's not what I want either. So how would I rotate it? Oh, 90 plus a little bit more, plus this much more. Okay, so let's measure this angle. I want to go clockwise, plus 30. Okay, so let's try 120-degree rotation. And let's change my rounding back, 0 decimal places. I'm going to rotate this object around this point. Okay, this is making sense. 120 degrees counterclockwise. That's cool. I could do it again. Rotate around this point, this object around this point, 120 degrees. Well, I kind of like rotating this object around this point. I don't know why all those angles just went on. Ah, I get it. Well, because I pushed the angle tool instead of the rotate tool, and it just marked all the angles. I didn't know it would do that, but that's kind of nice to know. So 1, 2, 3. Let's do it again. Let's reflect over the line and see if it works the way we expect it to. Reflect this over this line, this over this line. How many of these do I need? 1, 2, 3, 4, 5, 6. So am I right about that? That it is 6. So by reflecting or rotating around a point, if I reflect this over this line, will I get a regular hexagon? If I make 5 copies, okay, so remember when we made the polygon out of congruent triangles? We could take the area simply by finding the area of one triangle and multiplying by 6, or we can use 1/2 AP. Does this really have an area of 10? Maybe it does. 1, 2, 3. Let's change the color of this guy so it shows up a little differently. Ah, not what I wanted to do. But can I do no? So what I really want to do is change the color of the whole polygon. So right click on it over in the algebra bar and change the color of the whole polygon. Okay. Now 1, 2, 3, 4, 5. I'm going to make a couple more of these. Reflect about a line. And now I'm going to count 1, 2, 3, 4, 5, 6 of them. I don't really need this one. And I don't really need this one. I sure don't need these. But are we convinced that this hexagon, regular hexagon, has the same area as 1, 2, 3, 4, 5, 6 of these polygons? I wonder if I can make a polygon around this funky figure. I feel like I can. Yeah, okay. So where's that polygon? Let's change the color of it. Poly 10. Let's find poly 10. Let's change the color of it. Got a lot of compliments when I wore this color the other day, so let's make it bright blue. And poly 11 has an area of 10. Does that conform with the pink polygon? Has an area of 10. Okay. Okay. So here is the area of 6 congruent triangles that has the same area as the hexagon constructed of 6 congruent triangles. So I'd like to show, let's figure out exactly what I'm trying to show. I'd like to show that the area of 6 congruent triangles with base of x, let's say, and height of h is the same as the area of one triangle that has a base equal to 6x and a height equal to h. Which has the same area as a regular polygon with A equal to h and S equal to x. That is one side length is equal to the base of this triangle. Okay, so that's the goal with this illustration. And at this point, can I turn off some of these parallel lines, these y equal lines? Would that be less distracting? That is these x equal lines. Where are my lines? Here we go. X equal lines. What happens if I take them away? Okay, so now I'm looking for a polygon that has a base 6x and a height equal to the same height as these original triangles. So that's this new triangle right here. I'm going to put a segment here that we can call H. Let's go ahead and make it a dotted segment just for the fun of it. I don't need that point, that was an accident. Okay. Let's change the color of this polygon. What haven't we used over here? I've got blue. Okay, so we could use a green. Maybe if it were less opaque. How's that? And let's find it, and let's see if it has area 10, like the other two figures. Here it is. Polygon 10. So the area of the green triangle that has base 6 times the base of the smaller triangles, but the same height, has the same area as 6 triangles that have a base of x with the same height, which has the same area as the regular polygon that has the same height and a side length equal to x. So here's an illustration of 1/2 AP and the relationship between the triangles. So this illustrates the relationships between the related triangles and polygons, regular polygons in this case. That represent the various area formulas. We are also going to look at circles, chords, perpendicular bisectors, and finding the centers of circles. We have here chords from 2 circles. That is 2 chords from the same circle, just like you saw in class today. We'll use the perpendicular bisector tool to create a perpendicular bisector for each chord. Where these 2 bisectors intersect, we'll find the center of the circle. Let's see if it's true. Circle through 2 points. I can create the same circle through any of the endpoints of the chord, and the circles are identical. Let's try it again. Perpendicular bisector through this segment. Perpendicular bisector, pick the segment. I'm getting points. I need the segment.